Good morning. I'm Akash Reshan, 17BEC1065, here to present my third review of my OS project. Our project is called NAND to TETRIS, and in this, we will be building a computer from scratch using NAND gates. My teammate will take over.
This is Sriram N, 17BLC1045. Here, our project, which we're going to present here, is NAND to Tetris. In our project, we basically have 12 small mini projects which make up our project. So now we will be explaining one by one what each one does. Starting in the first module, in the first module, we use the basic NAND gates, which is already provided to us. Using that, we build all the other gates, for example, and 16-bit, DMUX, MUX, and so on, OR gate. Similarly, in the second module, we built the ALU. The ALU comprises of the full adder, half adder, and the increment operator, and each of this have been written in the HDL language, and we have used the gates which we've previously built in our first module. Now, the third module we use to make the memory of our system. In this, we use the basic bit which has been developed from the MUX and the D flip-flop which we previously constructed in our previous projects. And using a bit, we are able to create a register. Using 8 bits, we create one register, and using 8 registers, we create a 8 RAM 8, and using 8 RAM 8, we create a RAM 64, and so on. Similarly, for higher RAMs, we create RAM 4K using the next smaller values and RAM 16K, etc., and so on. Now, the next module, my teammate will continue.
Okay, so every computer is no computer without its hardware, and by that I mean the keyboard. So this module, we are basically creating the drivers so that the software can access the hardware, the keyboard that is, and all the keys present in the keyboard. So basically, the table which you see right now is the table which is used to reference the keys present in the keyboard to codes. These codes are basically the software part of the keyboard. So whenever you press, say, 1, the computer will basically get a code 49, and so if you press 0, the computer will get 48. So similar this is how the keyboard works. And the next module is the most important part of the module, that is the CPU. So what we're doing in this module is we're integrating the ALU and the memory unit. The memory unit has been explained by Sriram, and now I will be explaining the ALU unit. So what we're doing here is basically using an hardware simulator to simulate the chips that we have coded using HDL. And so basically we can see here there's a table. This table basically has all the various commands that the ALU can perform. For instance, when it's 101010, that means the output will be 0, and say the inputs are 0011, then the output will be -x. And this has been coded and has been implemented in our using HDL. And this window which you see in our left is the simulator. So what we do in the simulator is we have the code loaded, and we have a test case test case file loaded. So when we run this code with sample values, we will get, we can see it running over here. Yeah, so the code has been run. So now we can see the output of this code. So yeah, so this is the output of this code, and and this is the test files output, and we can clearly see that the output and the test file output are same, hence our values are working, and we can see the table over here. So hence our ALU is working. So now I will be explaining the CPU, which is basically the combination of both the ALU and the memory. So the diagram which you see over here is the block diagram of the CPU that we have constructed. I'll just briefly explain this now. So we can see the ALU is connected to a MUX16. This MUX16 basically contains a way to implement all the commands such as addition, negation, or all zeros, all ones, etc., etc. And the D contains the carry from the previous operation. And we also see a program counter over here. This program counter basically keeps track of which instruction is going on right now and increments after every instruction. So here we basically use HDL to code this, and the code will be shown to you now. So this is the code of the CPU, and this is nothing much. So basically, with the block diagram which we have basically used HDL to construct it, and you can see the MUX16 and the AND gates and the OR gates and the D flip flops, etc., etc. over here. So also there is a module called computer, much like a module called computer. So computer basically is the combination of both the CPU and the RAM and the memory. So we can see CPU, memory, and ROM. ROM is basically the permanent storage which can store their outputs permanently. So this is module 5, that the CPU and the computer. So the next module and is basically code conversion, that is converting a high level language to your basic level languages. Say take this for an example. Let's take Java for an example. So a Java has both an interpreter and a compiler. So when a Java program is written by you, the compiler compiles it to bytecode. And when this bytecode is sent to different computers, all the interpreters of the different computers interpret this code in different ways, and hence this is called two-tier compilation with both interpreter and compiler. My friend Sriram will explain more about this.
As Akash Reshan said, our Jack OS also uses a two-tier compilation of the code to transfer it from a high-level Jack language to the machine-level hack language. In between, we use three different converters, which is namely the assembler, VM translator, and the compiler. In the coming modules, we will see the building of these three. Basically, a compiler is used to convert the high-level Jack language that is written by the human into a middle-level language, which is an equivalent to a bytecode, which is also called as VM code in our case. And then this VM code is in turn translated into assembly language using the VM translator. The assembly level language is stored with .asm files. And finally, an assembler translates the assembly level language to a machine language, that is the hack file. The hack file consists of only zeros and one, that is, it's completely binary. Now we will see the working of the assembler. The assembler has pre-built syntaxes using which it is used to convert the assembly level language to a machine level language, which is in binary. So for example, if there is an assembly code which is md equal to d plus 1, we look it up in this table and see for the d plus m or m plus 1, we check, okay, so d plus 1 is here. So we take this part of the code, and this is the basic binary syntax. So C1 to C6 will go in that slot. And similarly, the first three are always ones, and the last three are used for the jump statements. And the D is all for the type of register used. So depending upon that, the entire syntax of the assembly language is not lost and is converted to a binary language. So our assembler here, let me show you a demo of our assembler. So we have a hardware simulator which helps in CPU emulator. we load our add program here, which is and here this program works by taking the input values which are supposed to be given at RAM locations 2 and 3. So right now I'll be feeding the values. At 2 I'll be putting a value of 13, and at 3 I'll be putting a value of 4. So now when you run this code, you can see over here in this gen GUI that you can see, as you see, 13 has been read, now 4 has been read, and you can see the ALU output here, it's 17, which is 13 plus 4. So from this, we can say that our assembler is working fine. Next, we have our translator. The translator, as I said earlier, is used to convert the VM code, which is the byte code, into assembly language. So this is the translator, and the translator has 4 different values, just commands which it has to use. So those are the arithmetic, memory, branching, and function. So these are the 4 types of commands that it has to handle in order to convert a VM language to assembly language. So let me show you a demo of this. We have already written our classes in Java and compiled it. So as you can see here, let me show you a demo of this. Is a test program which has already been provided to us by the course supplier. To run this code, we will be using again a CPU emulator, and we will load our Fibonacci series program, which is in module 8. And we also have a test file which can be used to test our output to the output which is already been provided to check the correctness of our program. So I'll be loading the test file here. As you can see, the test file has been loaded. And now I execute this and wait for our output. As you can see, the execution is in progress. Here we have 1100 clock cycles. So this is going to run up to 1100 clock cycles. We'll have to wait. So here we can see that our program has completed, and we can see that our comparison has ended successfully, which we can see here. We can see our output. So we have the first 5 values of the Fibonacci series which have been generated. Similarly, the compare file, you can see that the provided output matches our generated output, which tells us that we have correctly built our translator. Next, now my friend Akash will continue with the Jack language.
Okay, so basically every OS needs a language in which it's written. Linux has Java, and etc. etc. So basically, the language that we are using for our OS is the Jack OS. So the Jack OS is basically an object-based language. Basically, it doesn't have inheritance but has every other property of object-oriented languages. And this is a very simple language, and we can easily understand this language if we know Java. So it has many functions in Jack OS. I'll just name a few for examples. So there's absolute, multiply, divide, and minimum, maximum in the math function. And there are few string manipulation functions like new, dispose, length, caret, set, caret, and array, and etc. etc. We will be explaining these functions in the end, towards the end. So there are many functions like this. And So basically, this language is used to code our OS and all the functions in it, and we will be explaining these functions in the future. So my friend Sriram will now talk about the compiler, etc., etc.
Yeah. So the next module in our program is the compiler. Till now, we have seen how the VM code is converted to the assembly language and how the assembly language is converted to the machine language. So now the compiler is used to convert the high level language to the VM code. So we have again written this compiler as well in Java, and we've compiled it, and you can see that our files are present here. So we have been provided with a test code, and I will be showing you the working of it right now. Use a VM emulator for this. As you can see, we have a JAG file which has been compiled to a VM file here. So first we load the main file. So in this program, this program converts a decimal input to binary, and the decimal input was supposed to be given at RAM location 8000. So we go to RAM location 8000 first, and we given a decimal value, say for example 5, and hit enter. Now, if we run the program, we will be supposed to see now our program is finished running, and as you can see from RAM location 8001, we can see that and 8002 is 0 and 8003 is 1. So 101, which is nothing but the binary translation of the number 5 in decimal. So similarly, other numbers can be converted to binary, and as you can see, our compiler works fine. Next in our module is our final mini project, which is 12, which is also our OS of this project. And in this, we have 8 different modules. I'll be explaining one by one. First, we have array. The array consists of 2 different functionalities, which is new, which allocates memory for the new arrays, which is created, and deallocates, which deallocates the memory for deleted arrays. Keyboard has already been discussed in the previous module. Math, this handles all the mathematical functionalities which we required by our computer. So we have absolute function which takes in a value and converts it to its negative if it is a number which is less than 0. So it returns a positive number always. Then we have multiply, which is nothing but repeated addition. And we have divide, and here we use long division method to simplify and improve our time complexity. Square root, which is used to find the square root of a number. Max, to find the maximum of 2 numbers. Similarly, minimum to find minimum of 2 numbers, and so on. Next, we have memory, which has also been discussed earlier, and screen. Screen has the function of displaying the different outputs. So we have init, which initializes the screen initially, and we have clear screen option, and we have set color, which used to set the color in the screen. Draw pixel used to color each pixel in this given screen. And we have draw line, which is used to draw a line from the given coordinates x1, y1 to x2, y2. And these are the coordinates. In case x1 is greater than x2, it's used to interchange both, and so that always x2 is greater than x1. And we have horizontal line and draw vertical line, which has been described down below here. Horizontal line is used to draw a horizontal line if both the y coordinates are same, then a horizontal line is drawn, and similarly, if an x coordinates are same, the vertical line is drawn. And we have a draw rectangle, which is a combination of the horizontal and vertical lines, and so on. Now, Akash will explain the remaining modules.
Okay, so I'll be first explaining the output module. Basically, the output module is in charge of getting an output into the screen. That is basically like when you type something, the output has to come to the screen. So basically, generating characters, strings, etc. So there are many functions in this output class. The first function I'm going to be talking about is the init function. The init function basically initializes the screen, and you can see over here the screen has been set to 16,384 bits, and it also sets the cursor to the origin, basically 00. So the next function is the one of the most important functions in this, and that's the init map. So what does the init map do? The init map basically generates a bitmap for each character, that is say your letters, your symbols, your quotation marks, your exclamation marks, etc. And for each of these, based on the keyboard's values, it will basically map it to a bitmap. So that is seen over here, and all of these has been created. uh, yeah, so after this, there is the print char function, which basically prints a character. How does this do this? It refers to the bitmap and checks whether when, so say you're clicking A, it will get a value will be created, and this value will be compared in the bitmap. And when hit has been when it matches a value, it prints the letter based on the map. So that's how the print char function works. And then there is the print string function, which is basically a string of characters, or basically many characters are placed together. Then there is the print function, which is used to print an integer. And then there's a println function. So what does a println function do? The println function basically prints a string, and then shifts the cursor to the next line. Also, I forgot to tell this. So in the print char function, there is a the cursor. So what the cursor does is, after every character, the cursor moves by one space ahead. Yeah. So after that, there's the backspace function. So the cursor moves one place back, and the character at the previous place is removed. And yeah, that is the output module. So next we'll be seeing the string module. So basically the string module it takes care of all the string manipulation and string creation part of the OS. So there's the new function of the string, which is basically used to create a new string, and then based on the max length, etc., etc. So there's a dispose function, which is used to dispose of a already created string, and free up space for other stuff. There's the length function, which is used to find the length of a string. There's a caret function, which is used to find the character at a given index, and there's a set caret function, which is used to replace a given character at an index with another character. And then there's an append char function, which is used to add one character at the end of a string, etc. So that's the another important thing is the int. Another important thing is the Okay, so there is the int value function, which basically checks, which basically returns the value of the string. Say you type the number 9. Now this is basically a string, but we need it to be an integer so that we can use it in arithmetic calculations. So we basically subtract 48, which is the ask sorry 45, which is the ASCII value of the 0. So basically, if it's 9, the ASCII value of 9 is 54 minus 45, that's 9. So we will basically get the value of the string as an integer. Similarly, there's a int to string command, which is used to create strings using an integer, same way you just add 45. And there's also other commands like setInt, which is used to set an integer at a given value, and etc, etc. So there's a new line function which basically gives a new line, and the ASCII value of this is 128, etc., etc. Thank you. So the next is a sys function. This is basically the main function of sorts. All it does is initialize every hardware and wait for it to get ready. One of the most important functions over here is the delay function, which is used to create a delay so that the software and the hardware can set up itself for operations. There's also the error command, which returns the error code uh, and halts the program when an error has been encountered. So this is basically all our modules. Now we will be showing you few modules that we will simulate. Sriram will be simulating the first module.
So now I will show you a small demo of how our compiler works. Now, given that our compiler converts the high-level language to VM files, we have a set of files which we just explained to you. As you can see, are all JAK files, which are high-level language files. So now I'll be converting this using our JAK compiler, which is we discussed in module 11. We use the command java JAK compiler with our directory name, which is OS files in our case. And let me open this file for you. So as you can see, when I hit enter here, you can see the command prompt that all these files are created. And simultaneously, you see that for each JAK file, a corresponding VM file has been created. So this is how our compiler works. Now I'll show you certain demos of using the test files which have been provided for our OS. So firstly, there's a screen test which has been provided. And we need a VM emulator for this. So we'll load this main program to the VM emulator, which is in screen test main. And so once we load this and we start running it, we can see that house is generated here on our output screen. And the given test output, as you can see, this is given by the course developer. And as you can see, we have successfully managed to recreate this image on our code, and the code which has been compiled by our compiler. So we can say that our compiler is working fine. Now, just to make things sure, my friend Akash will be showing another test.
Okay, so I will be showing you the output test. So what this test basically does is check whether the screen is working and the keyboard is working and the display is working, and whether all the characters have been set properly. So basically we'll be using the same emulator as before, the VM emulator. So we will open the emulator, we will load the script into the emulator that is in the output test folder. And now we will run it. Yeah, so as we can see over here, all the characters have been printed over here, and these characters, if you remember, have been created using the bitmap that we generated in the function. So we can see that this and the test output that has been given by the
Supplier.
course. Okay, fine. Okay, as you can see, it is seen that both the output that we have gotten and the output given by the course providers are the same output, and this concludes that our screen is working and all the characters have been successfully mapped by us. So this concludes our project. Now Sriram will be starting with the conclusion.
So as you can see that we have successfully built all the modules in our project. So we'll be giving a top-down approach of what we've built. So first we write a high-level Jack language program into our computer, which by the help of our OS, and then the compiler is used to convert the Jack language into VM code, which is the bytecode equivalent, and then which is in turn converted to machine language by help of the VM translator. And then we convert the machine language to hack language, which is the machine language which is in binary using the assembler. And from now, Akash will explain the remaining.
Yeah, so basically, what happens after this is the bit level, we can say, of the program. So what the machine language does is convert everything to binary, as we know. So when we have it in binary, we can process it using our basic CPU RAM models that we created using HDL. So basically, all of these will basically process the data. So how we created these CPU RAM and all was using our elementary gates like, yeah, the adders, muxes, etc., etc. So those have been done. And how did we create these muxes, and gates, adders, half adders, etc.? Basically through our NAND gates, and hence concluding our project NAND to Tetris. And by this we can say